Hey everybody, welcome to the weather breakdown. Today is January 8th, our fifth video of the year, and currently Storm Goretti is bashing the coast of England and France. So let's take a moment here and look under the hood, so to speak, see what's inside, and admire the storm in all its glory. Let's not waste any more time and take a peek under the hood, shall we? Now, what we see here is Goretti in all its glory. We have the magnificent comet shape here. We have the low pressure center situated right there. You can see the magnificent boundary here, obviously signifying the cold front. We have our warm front extending like this and the occlusion extending like that. Now, if we draw the conveyor belt model here, we can draw the conveyor belt like this, where there's a branch off moving here and a branch moving towards that direction. This is the warm conveyor belt. This is a supply of warm, moist air into the system. All right. We have our cold conveyor belt. This moves under the warm conveyor belt, moves into the cyclone like this. This is the cold conveyor belt. And we have another airstream in our cyclone here, which is this one. And this one is called the dry intrusion. Now, as this air in the warm conveyor belt moves along the cold front, it starts to rise. And when it rises, it reaches lower pressures, leading to colder temperatures, leading to condensation. And when this juicy air starts to condense, it creates or releases rather latent heat. And that latent heat actually warms the air mass. It warms this air mass here, right, in the warm sector. Okay. Now, when it warms this air mass, this means that there's a bigger contrast here between this air mass here and the air mass behind it. What that leads to is that leads to a strengthening of the jet in between these air masses here. You can see this actually by the spacing of the 500 millibar geopotential height contours. If you want to learn more about it, I created a dedicated video on it. It will be somewhere, I don't know, here or there. I don't know yet. Click that video if you want to learn more about it. Now, the cold conveyor belt, this one also rises, but less steep. So this one also rises here and curves around the low, moving towards that direction. Now, the dry intrusion, this one doesn't ascend, this one descends. It moves towards the ground. Now, as it moves towards the ground, there's a process which is called adiabatic compression. This adiabatic compression means that the parcel is being squeezed together. Why? Because the air parcel, as it descends into the troposphere, meets higher and higher and higher pressures, squeezing the parcel together. If it squeezes the parcel together, the temperature increases, and the temperature increase leads to drying of the parcel. And you can see that actually by the darker brightness temperatures here in the water vapor imagery. Now, yesterday we've talked about an IPV anomaly that was going to be superimposed with the surface low here. Okay. Now I created another cross section for you where we can show this. So let's dive into the cross section, shall we? So what I've done here, guys, is I created a cross section straight through the center of the cyclone to show you the superposition between the IPV anomaly, the upper level feature above, upper level forcing feature above, and the surface low. Okay, so what I'll do first, I'll first pan a little bit the map and rotate a little bit so you can create a mental picture in your head what we are actually looking at. Okay, so let me pan the map here, right? This is from this perspective. Let me rotate a little bit. Oh, there's thunderstorms going on in the cloud head here. This is also a good video, actually, but let's not delve into that one because it'll be a long one. So we'll look at it from this perspective. Let's rotate a little bit further towards this perspective because it's much easier to understand. Okay, so we have our large frontal boundary here, our large cold front here, leading into the warm front and the occlusion leading to the center of the cyclone there. Now, we can see a number of things here. Number one, along the edge of the cloud head here, you can see a abrupt climb in vertical extent in the cloud field here, up to 10 kilometers and higher. Right? This is observation number one. Look how abrupt this vertical climb is. It's massive. What we can also see is yesterday we've talked about an IPV anomaly that was more or less going to follow the isotropes towards the east. And we already mentioned here that yesterday, or we saw yesterday, that the IPV anomaly was situated at more or less 7 kilometers high above the surface. Yesterday, we also mentioned that as the IPV anomaly moves towards the northeast and catches up with the surface low, that it would start to descend. And you can see already that indeed it started descending. It already descended like 2 kilometers since yesterday. Okay, that's observation number one when it comes to the IPV. And observation number two is we also mentioned yesterday that the isotropes are going to be spread further apart, which you can also see. The isotropes are already spread further apart. Now, when the IPV anomaly gets into that region where the isotropes are spread further apart, static stability decreases. And since PV is a conserved quantity, the effect of that is that vorticity must increase. So what we have here is we have a vorticity field at 500 millibar that is intensifying. Okay, now as this vorticity field intensifies, this creates an avalanche of effect leading to a runaway effect. And it's this runaway effect that we're going to talk about here. So as this vorticity increases, it pulls in more and more and more air because you can see it as a cogwheel, right? This is the conveyor belt model. It pulls the conveyor belt harder towards the north. Okay, so this conveyor belt starts to accelerate towards the north a little bit faster. Okay, as it moves towards the north, as we've already mentioned, this starts to rise here. As it rises, it starts to condense because it's moist air. Actually, this moist air starts to condense. If it starts to condense, what happens? Latent heat release gets released where it starts to condense. Latent heat release releases warmth into the atmosphere. Okay, as this latent heat release happens, this means that this air mass is warming even more, creating a higher contrast with the cold air mass. Okay, as it creates this higher contrast within the cold air mass, it creates a stronger jet stream. Okay, it creates stronger jet stream in the upper levels of the atmosphere. Rather, if the jet stream increases, what's also happening is due to the jet increasing, upper level divergence starts to increase massively. Okay, when upper level divergence decreases, what happens below at the surface? Low level convergence happens. Okay, when low level convergence happens, then this sets up a vertical motion here up into the atmosphere, right? When this vertical motion happens, it stretches the vorticity column, and it's like an ice skater. When you stretch a vorticity column, the column decreases in diameter, increasing vorticity. So here we go again. The cycle continues. Vorticity increases. What happens? It pulls in more air to condense. Okay, more air to condense means the contrast between these two air masses starts to increase as well, leading to a faster jet, leading to more upper level divergence. Okay, leading to more upper level divergence now, leading to more low level convergence now, leading to more upward vertical motion, right? Leading to more stretching of the vorticity column, leading to even more warm, moist air that's being pulled in, leading to even more condensation, leading to a faster jet, leading to even more upper level divergence, leading to even more low level convergence. And you know where this is going, right? Leading to even more upward level motion, leading to even more vorticity stretching, leading to even more pulling in. It's the feedback loop actually that's going on. And this is how rapid cyclogenesis actually forms. And this is why the storm is so potent. You have all these ingredients perfectly stacked on top of each other. Okay. And this process will keep continuing and keep continuing and keep continuing. And this leads that the cyclone will deepen and deepen and deepen further until this guy here, until this line here starts to move away from here. Okay. Why? Because this pulls the vorticity away here from the system. So if you decrease the vorticity, you actually slow the engine down. When you slow the engine down, the whole process starts to decay, leading to a filling of the low pressure center, leading to a weakening of the wind field, leading to the demise of the system, essentially. You already have this mental model now. So in future cases, when rapid cyclogenesis cases happen, I might do the same deep dive here, and you will see all these similarities in repetition. Okay, the more you see it, the more you start to understand it. With this, I'll close off the video and I'll see you in the next one. Bye, everybody.